Hello everyone. Today we are going to start with the PYQ series for NEET, and the first topic is haloalkanes and haloarenes. So let us start with the PYQs from this chapter, and the first question is, what is the ayurvedic name of the organic compound formed in the following chemical reaction? Now we have acetone, its reaction with ethyl magnesium bromide followed by hydrolysis, and you need to tell me the ayurvedic name of the product. Now, we know we have started the preparation methods of alcohols, and there we studied that the reaction of formaldehyde with Grignard reagent followed by hydrolysis results in the formation of 1-degree alcohol. The reaction of aldehydes other than formaldehydes, or say acetaldehyde, when reacts with Grignard reagent, we end up getting, followed by hydrolysis, we end up getting 2-degree alcohol. And the reaction of ketone with Grignard reagent results in the formation of 3-degree alcohol. So here we have acetone. So let us discuss this reaction. We have acetone. Acetone, when reacts with ethyl magnesium bromide. Now we know that magnesium is electropositive in nature, and this ethyl will act as a nucleophile. Basically, this will have a partial negative sign for obvious reasons, because metal is electropositive in nature. So this is negative, and obviously this is positive. Now, the next step is attack of this C2H5 ion on this carbonyl carbon, and this bond shifts like this. We know that this carbon is electrophilic in nature. Why? Because of the high electronegativity of oxygen, the polarity is generated in this bond. So what we get is something of this sort. And here we have C2H5. Obviously it is balanced by Mg plus Br. In the next step, there is hydrolysis. So basically what we end up getting is this alcohol. Why? Because we have CH3CO minus MgBr, and we have while performing hydrolysis, what we have is H plus and OH minus. So what we are getting is CH3COH, CH3C2H5 plus we have magnesium hydroxybromide. So what is the ayurvedic name of this? The ayurvedic name of this is 1, 2, 3, 4. So basically this is, so how can I write it? I can show it like this. So this is 1, 2, 3 and 4. So this is 2-methyl. This is 2-methyl-butane-2-all. So 4th is the correct answer. 2-methyl-butane-2-all is our product. I hope you understood this. Let us move to the next question. The next question is, the major product formed in dehydrohalogenation reaction of 2-bromopentane is pent-2-ene. So we are given the reactant as well as a product. So this is 2-bromopentane, and we are performing the dehydrohalogenation. Basically, we are performing the dehydrohalogenation, and what we are getting is pent-2-ene. This is pent-2-ene. Now we know that this particular reaction, this is basically an elimination reaction or beta elimination. So this elimination reaction happens in the presence of an alcoholic base, or we can also say that it happens in the presence of a strong or bulky base for say alcoholic KOH. And what happens is, basically this is your anti-elimination. So what happens? Suppose if we have this, now in the first step, the base abstracts this hydrogen, this bond shifts here, and this leaves. So basically, this is your alpha carbon, the carbon which contains this halogen atom. The carbon adjacent to this is beta. Now we have two types of beta. This is beta and this is beta dash. So basically, the base can abstract any of these beta hydrogens. But I preferred this to this. Why? For obvious reasons, because if I abstract this particular hydrogen, I end up getting a more stable alkene, that is a more substituted alkene, and that alkene is governed by the Setzeff rule. So Setzeff alkene is basically the stable one and the more substituted one. So what I am getting is CH3, CH double bond CH, CH2, CH3. So this is your Setzeff alkene. That is the more substituted one, the more stable one, because we have more number of hyperconjugative structures are possible because of the presence of more number of alpha H. Now here, if I abstract this particular hydrogen, I end up getting the less substituted alkene, which is less stable, and we call that particular alkene to be the Hofmann alkene. We get Hofmann alkene in the case of elimination reaction, but that is when there is the presence of a bulky base. We know that bulky base cannot attack on this hydrogen for obvious reasons, because it will get steric crowding, there will be the steric hindrance, so it will attack from the least substituted side. Okay, so the answer to this question is Setzeff rule. Now Hund's rule, we studied the structure of atom, Hund's rule of maximum multiplicity. Hofmann rule we have just discussed. Huckel's rule is for the aromaticity. So this is the Setzeff alkene, and Setzeff rule governed the formation of this type of alkene. I hope this is clear as well. Now let us move to the next question. The next question is, the major product of the following chemical reaction is. Now, we are given an alkene and its reaction with hydrogen halide, that is hydrogen bromide, HBr, in the presence of benzoyl peroxide. Now this is your benzoyl peroxide. So basically, this is your benzoyl peroxide. We know that benzoyl peroxide or these peroxides, they are good radical generators. So this particular reaction, this particular addition takes place via free radical formations. So we know that this bond breaks homolytically. What we get is C6H5 C double bond O, free radical. In the next step, this bond breaks homolytically. I get a free radical here. This free radical forms a bond and CO2 is released. And what I get is this phenyl free radical. Now this phenyl free radical, when reacts with HBr, this bond breaks homolytically. I get a free radical over here and free radical over here. So C6H5 free radical combines with H free radical to form C6H6 plus I get bromine free radical. So this peroxide is basically the radical generator. So this reaction basically, this reaction follows free radical mechanism. There is no carbocation formation like the usual addition of HBr, and so the product here is governed by anti-Markovnikov rule. So the product here is governed by anti-Markovnikov rule, which says that the negative part of the attacking species of this adding molecule will attack on that carbon, will attach to that carbon which is having more number of hydrogens, which is contrary to the Markovnikov rule. And we know that anti-Markovnikov rule never fails. So what we are getting is, when we are attaching the bromine free radical to the terminal carbon, so A is the right answer. We cannot form this. Now why A is the answer? Because when I take this alkene, or let's say any alkene, let me take this particular alkene. Suppose I have this alkene. Now I have got the bromine free radical, so this bond breaks homolytically like this, free radical, free radical. Now I have two options. This can attach with this, or this can attach with this. So let us see both the possibilities. One possibility is this, and I end up getting this type of free radical. The other possibility is this, when the bromine free radical couples with the terminal carbon, and this is what I get. So by doing so, I get a 1 degree free radical and I get a 2 degree free radical. I know that 2 degree free radical is more stable, so the reaction proceeds via this free radical. I have H free radical, they both combines, and what I get is CH3, CH2, CH2, Br. So this is my final product if I had this type of alkene. So this type of alkene plus HBr, this is your basically electrophilic addition reaction, and in the presence of peroxide, which is also called Karash effect. And there is one more point to note, that this peroxide effect is observed only in the case of HBr. We do not talk of this peroxide effect in the case of HCl. So if it would have been HCl, so peroxide won't affect our product, would not have affected our product, and the product would still be governed by what we say, the stability of free radical, which says 3 degree is more than 2 degree is more than 1 degree. So please note that peroxide effect is only observed in the case of HBr, because in the case of HCl, the bond strength is high. So we cannot break the bond homolytically in order to get chlorine free radical. And in the case of HI, though we get iodine free radicals, but those iodine free radicals, they couple and form iodine. They just couple and form iodine. So only HBr is left, and peroxide effect is observed only in the case of HBr. I hope this question is clear. So let us move to the next question. The next question says, we have a compound, the compound is C7H8, undergoes the following reactions. Now see, so basically C7H8, how to comprehend it? First of all, let us see the options. We have toluene, toluene, toluene and toluene. So let us try with toluene only, or we can also do it in this manner, that whenever the difference is less, see C7, so always look for the benzene ring first. So C7H8, this is toluene, C7H8, this is your toluene. Now toluene on 3 times chlorination in the presence of heat. So basically, chlorination, halogenation in presence of heat or light, it results in the, what we say, side chain substitution, or we can also call it benzylic substitution, or we can also call it allylic substitution. In this case, it is benzylic substitution. So basically, this is for side chain. And 3 times chlorination means that the 3H of this CH3 are replaced by chlorine. So we are having something of this sort. Now, what is this? This is benzo. I have this benzo trichloride. This is benzo trichloride. Now, we know that in toluene, CH3 group is ring activator. Now, if it is ring activator, so if I would have performed, this is basically the halogenation, electrophilic substitution reaction in the presence of AlCl3 or FeCl3. So this is halogenation. This is your electrophilic substitution reaction. So if I would have performed this A to B from toluene, if I would have performed the halogenation on toluene, I would have got ortho and para substituted product. Why? Because CH3 is ortho-para directing group, a ring activator. But now I have got this C with C3Cl groups. Now this group is highly deactivating. This is highly deactivating. This is now electron withdrawing group. And if it is electron withdrawing group, it is decreasing the electron density of this benzene ring. It is deactivating the benzene ring. So what will happen? And we know that in the presence of electron withdrawing group, the substitution takes place at the meta position. So this is basically a meta director. So bromine will attach to this, will be substituted at meta position. This is my B. So this was my A and this is my B on halogenation. Now the next is zinc in the presence of HCl. Now this is a very common reducing agent. This helps in the reduction of alkyl halides to alkanes. We have started with the preparation of alkenes also. We can take zinc HCl, we can also have iron HCl, we can also have zinc copper couple in the presence of alcohol. So many reducing agents for the reduction of alkyl halide to alkanes. So what I am getting is, after this reduction, this step is reduction, this is reduction. So I'll get CH3. So basically what happens, CX bond gets reduced to CH bond. As simple as that. So I get metabromotoluene as the product. So this reaction is very important. Important for the reason that you cannot end up getting metabromotoluene if it would have been the direct halogenation. So this is a unique reaction and a beautiful reaction, you must say, that I am ending up getting metabromotoluene from toluene. So this is how I get it. So I consider this question to be a wonderful question. So I hope you have got this question. Let us move to the next one. This is the next question. Identify A and predict the type of reaction. So we have this substrate molecule, we have this reacting with NaNH2. This is basically a base. Okay. This is sodamide, and we also have, so it provides us with the nucleophile also, this amide I. Now what happens? Let us see. So we know that haloarenes, they are quite unreactive towards nucleophilic substitution reactions, and we have the tendency that whenever I say nucleophilic substitution reactions, what the first thing that comes to our mind is SN1 or SN2. But in the case of haloarenes, for say chlorobenzene, if I have chlorobenzene and if I perform the nucleophilic substitution reaction, for say if I have NaOH, you know that this reaction doesn't take place and you don't end up getting phenol. Why? Because this is quite unreactive towards nucleophilic substitution reaction for obvious reasons, because here the Cl is attached to sp2 hybridized carbon and the lone pair of this chlorine are involved in the delocalization with the benzene ring. So we have partial double bond character in this bond. And why the substitution reactions cannot take place via SN1 or SN2 is SN1, because you know that after the removal of the Cl, I end up getting phenyl cation, which is highly unstable. And also because you are having positive on the sp2 hybridized carbon, which is unstable. And secondly, not via SN2, because this benzene ring is offering you the steric hindrance. So basically, SN2 is also ruled out. So basically this substitution takes place, but this substitution takes place under drastic conditions of temperature and pressure. So you must have seen it as 623 Kelvin, 300 atm pressure, and you end up getting phenol. But my question is that what is the mechanism follows here? You must have read it, Dow's reaction. But my question is that what is the mechanism followed here? So the mechanism followed here is your elimination addition reaction. Basically this is substitution only. But substitution takes place via elimination addition type mechanism. And here I end up getting unstable intermediate which is benzyl. Now let us see this particular reaction. So suppose I have this. I have this OCH3 group and Br. Now in the first step, I have this orthohydrogen over here. So what happens? See. So basically, I have the base NH2 minus. This will abstract this hydrogen, right? After abstracting this hydrogen, what I get is something of this sort. Negative over here and Br. In the next step, this bond shifts here and this Br leaves. So what I get is, this is my new intermediate form. This is the intermediate benzene. Now, this benzene is we say this is unstable. Basically, because the third bond is not strong. Why it is not strong? You must be wondering that the electrons of this bond must be involved in the delocalization with the benzene ring, but it doesn't happen. Basically, the electrons of this bond, they are in the sp2 hybrid orbital of the carbon present in the ring. So the electrons are in the plane of the ring, and they are not involved in the aromatization or delocalization with the p orbitals. So this is a weak bond, and if it is a weak bond, so suppose if I have a force, so I need to break this bond. Now we have two possibilities. Obviously, I have this. Now we have two possibilities. I can break it in this manner, that I have a negative over here and a positive over here, or I can also break it in this manner. That I have negative over here and positive. So basically, the formation of carbonyl, for the formation of carbonyl, I have two possibilities. Just now I said that this negative, now see, so basically this OCH3 is plus M group, this is plus M and as well as minus I. Plus M because the lone pair of electrons on oxygen are involved in the delocalization with the benzene ring, and minus I because of the electronegativity of oxygen. So plus M is ruled out. Why? Because I'm not talking about the delocalization, because this bond, the electrons of this bond, they are not involved in the delocalization. So I have only minus I. So if I consider the minus I, you see that we know that minus I, the carbonyl stability is directly proportional to the presence of electron withdrawing groups, because I need to disperse this charge. In order to make it stable, I need to disperse this charge, and electron withdrawing groups help in the dispersal of this charge. Whereas electron releasing group, they helps in the accumulation of this charge, intensification of this charge. So what I am doing is, so this OCH3 is stabilizing the negative, and since you know that inductive effect is distance dependent, so obviously I will consider this particular species to be more stable than this. So this is not formed, this is formed. Now this is the major one. So what happens? Now I have this. Now I have this. Negative. And here I would have positive. There, this NH2 will have a tag. In the next step, what happens? I know we have ammonia. We have basically ammonia also in this case. So H is abstracted from there, and what I get is this as the major product. This as the major product. So not this, no, not this, because carbonyl at meta position is not that stable when it is at ortho position. So this is ruled out. Definitely not. This is also definitely not. OCH3 is sign substitution? No. Sign substitution? No. Sign substitution is basically the substitution of NH2 at the position adjacent to this Br. So this is now I have D. So D is substitution. Yes, D is the answer. So D is the answer. So this is basically addition elimination type mechanism. The mechanism is elimination addition type. The reaction is substitution only. So the substitution reaction takes place via elimination addition type mechanism, where I end up getting, where the reaction, the mechanism is the mechanism proceeds via the formation of this intermediate benzyl. Now the next question is, consider this reaction CH3CH2, basically I have propyl bromide in the presence of NaCN. So you are replacing Br with the Cn, and you know that this is primary alkyl halide, and this is basically for the nucleophile, and you know the Cn minus basically the Cn minus is an ambident nucleophile. Why? Because I have this carbon end also, and I have this nitrogen end also to behave as the nucleophilic site. So you know that between carbon and nitrogen, carbon is a better nucleophile for obvious reasons, because it is less electronegative and hence more donation is possible. So the attachment is from the carbon center. So this is one thing. The second thing is that this is a substitution, and you know that in the case of primary alkyl halide, SN2 is generally favored. So this is basically your SN2 type of substitution. Now, so we must be knowing that SN2 mechanism, basically it's one of the important features that SN2 mechanism is favored in the presence of polar aprotic solvent. It is favored in the presence of polar aprotic solvent. Polar aprotic solvent. For example, we have acetone. The bond is polar, but it is aprotic because I do not have H attached with electronegative O. Other examples being THF, other example being DMF. We have DMF here, dimethyl formamide, which is something like this. This is your dimethyl formamide. The next example is DMSO. We have DMSO, which is dimethyl sulfoxide. This is DMSO, dimethyl sulfoxide. So in the presence of these aprotic solvents, we have ethers. Ethers are also aprotic, but they are not polar. So because I need the polar medium, and I do not require H plus. So polar aprotic solvent. So these are your, for say, CH3CO, CH3, DMF, DMSO. Any of these. Ethanol, methanol, water, you know that they all are polar aprotic solvents, and SN1 reactions are favored because it helps in the solubilisis of the carbocation formation over there, the carbocation formed, and also the leaving nucleophile. So we require the polar aprotic solvent in the case of SN1. Here, SN2 way, we know that this is only one step process, no intermediate is formed. So I do not require the solubilisis of anything. We just have the transition state. So the next question is the reaction of, this is given with HBr. Again, the reaction of alkene with HBr, let us see. So we have this. C6H5 is basically this phenyl ring, and what I have is CH, double bond CH, CS3 plus HB. Now we know that addition of hydrogen halide is governed by the Markovnikov rule. Basically, Markovnikov rule fails when there is a possibility of rearrangement of carbocation. So it would be better if you if you consider the stability of carbocation to be the governing factor for the product. So according to Markovnikov rule, you know that. Now in this case, let us see. So let us proceed via the formation of a carbocation, and then we will look for the stability of carbocation. That is there any possibility of rearrangement so that I can end up getting even more stable carbocation. So see, I have two possibilities. I can have positive over here, I can have positive over here. But I know that positive over here is very stable because this is your benzylic carbocation, and this is stable by the delocalization of electrons from the benzene ring. So this is favored and this is not favored. So if this is favored, definitely the negative part of the addendum will attack on this particular carbon, and this shifts like this. So what I am getting is this. This is what I get. So bromine adds to the benzylic position. So I have C. the answer. I hope this is clear. So C is your major product. You know that addition of this HBr is your regioselective reaction. Regioselective is when you have two possibilities for the products. One is major, one is minor. So this is your major and this would have been minor. Clear? Check. So the next question is, in an SN1 reaction on chiral centers, there is inversion more than retention leading to partial racemization, 100% retention, 100% inversion, 100% racemization. Now, SN1 reaction basically, now when you start with a chiral substrate molecules, per se, suppose I have something of this sort. This is my chiral substrate molecule. The first step is a slow step. You know that the first step is a slow step. The first step is a slow step. This is the rate determining step. And where this X leaves. So once this X leaves, what I have is this. And now this structure is planar. You know that this is trigonal planar. Now I have the geometry to be planar. If it is planar, then I have that for example, if the attacking nucleophile is OH minus. So let me write in general any nucleophile. Now it has two possibilities. Either it can attack from backside or it can attack from front side for obvious reasons because this is planar. Now, if the probability of backside attack and the rear attack is same, then I would say that there is 100% racemization. Definitely it's not 100% inversion, which is the case in the case of SN2. It is not retention, 100% retention, because the backside attack is also possible. So now, if it would have been 50% and 50%, that would be the overall optical rotation. You would have that would have been 0 and racemic mixture, racemic modification. So what you had, you would have 100% racemization. But you know what happens? Basically, in the solution, because I know that this reaction is favored in the presence of polar protic solvent. So what happens? The X that leaves, that is in the vicinity of this carbocation. And we have, you know that they are bound by the electrostatic force of attractions. So basically, the front side attack is somewhat hindered. This is somewhat hindered. When I say somewhat hindered, it means that the backside attack, for say it is 60% and the front side attack is 40%. Right? So that is the backside, there is inversion more than the retention leading to partials, because this is not 100% racemization, 50-50. This is for say 60% and 40%. Now there must be a question that why this front side attack is taking place. Now this 40% is possible because the polar protic solvent is actually stabilizing this anion, stabilizing this halide ion by solvolysis, like this. So this is surrounded by water molecule. So this is stabilized, and if it is stabilized, so I can say that these water molecules, they sits in between the carbocation and halide ion, and they are breaking. They are basically weakening these forces of attractions, and hence, and this polar protic solvent is not only stabilizing the halide, it is also stabilizing this carbocation. So basically, this water molecule sits in between. The attractive forces are somehow weakened and front side attack is possible. So this, but it is always less than the backside attack, because during the backside attack there is no such hindrance. So it is inversion more than retention leading to partial racemization. The next question is, how many stereoisomers does this molecule have? How many stereoisomers does this molecule have? Now, it is CH3, CH, double bond CH, CH2, CH, Br, CH3. Now, stereoisomers means that you need to report geometrical isomers as well as the optical isomers. So, geometrical isomers. Geometrical isomerism is basically the cis-trans isomerism. So, here we have a double bond. So, there is a possibility of cis and trans. So, we have cis and trans. So, we have two geometrical isomers. Plus, for optical isomerism, we need to check for the chiral carbon. Is there any chiral carbon? So, we see that this particular carbon is chiral because all the four groups are different. The four valencies of carbon are different. This is sp3 hybridized and all the four groups are different. So, if all the four groups are different, so we can have, we have R configuration as well as S configuration. R and S, basically they are non-superimposable mirror images of each other, what we call enantiomers. So we got two optical isomers from here. So in total, I have two geometrical isomers, two optical isomers. So it is 4. Answer to this question is 4. Okay. Now let us discuss the last question of this video, and then we will continue with our series in the next video. So the last question is: this is your molecule CH3, CHCl, CH2, CH3 it is having a chiral center for obvious reasons because it is sp3 hybridized and all the four groups are different. Now, basically this type of representation is your Fischer representation. This is a Fischer projection formula. In the Fischer projection formula, this vertical line is basically your, or you can write it this way, that this vertical line, there's a vertical line, there's a horizontal line. The vertical line is basically the back. We just represent it like this, that this is the back side, and the horizontal line is the representing the front side. So this is how you represent it. So anything, so this is how it is written. Now, let me write it in this way. So this is how the Fischer projection formula is written. Now, so let us see. Now, in order to write the configuration, we need to look for the priority order. Now, the priority order of the four groups is in accordance with the atomic mass or atomic weight. So we know that in the first one, this is my first molecule. This is my first representation. We know that Cl is having the maximum atomic weight among A, B, C, D. So let us give this number 1. Now then we have C2 and C. So basically you need to write it in the open form. This is C2H5. This is how I write. So H is definitely the last one. So between CH3 and C2H5, it is C, C. Then move ahead. H, H. But here we have C also. So we give this the second priority, this the third priority. Okay, and definitely this is the last one. We do not want to write the last one as well. Now, it is not necessary to write the last one. So now what you do? Move from 1 to 2 to 3. And if it is clockwise movement, the configuration is R, and if it is anti-clockwise, the configuration is S. Now, there is one more thing to note. If the least priority group is on the horizontal line, you need to change the configuration. Suppose in this case, whatever. So what is the configuration? 1, 2, 3. This is your clockwise. So clockwise is R. So it should have been R. But since the last priority group is on the horizontal line, you need to change the configuration, make it S. So the answer is S and not R. The answer is S and not R. So the first one is having the S configuration. So what I said is that the last priority group, if it is on the horizontal line, then you need to change the configuration. Reverse the configuration. In the second one, what it is, but you are supposed to report the R configuration. In the second one, this is 1, this is 2, and this is 3. So this is again, this is clockwise and H is on the vertical line. No need to change the configuration. R remains. This is R. So I think this is the only answer. The third one, this is 1, this is 2, this is 3, This is your R, since this is clockwise, but since H is at the horizontal line, this is S. And in the last one, this is 1, this is 2, this is 3, this is anti-clockwise, this is S. And you do not have to change it to R. Why? For obvious reasons, because H is on the vertical line. So this was the last question of today's series. So we will continue with question number 11 in the next video. I hope you have understood all the 10 questions, the concepts behind it. Thank you so very much. Thank you.